Good afternoon, everybody. We have seen already the part that is FET biasing. We have again repeat the same part for revision purposes. That is what do we mean by FET biasing. See, when we have to operate the field effect transistor, right? Operating indicate that for the different purposes of the field effect transistor. That's why we have to use the field effect transistor, right? When we have to use the field effect transistor, in that case, one of the important thing is that it have required the biasing. Biasing means applying voltage to the respective terminal of the field effect transistor to work in a particular condition. Okay, accordingly, there are three fixed bias configuration. One is there are three biasing configuration of field effect transistor. One is fixed bias, other is self bias, and third is voltage divider biasing, right? These are the three configuration. It has some of the advantages as well as disadvantages. Accordingly, they have to be used and according to need of ourselves. Okay, so fixed bias configuration, we have to apply the fixed voltage across the devices. In case of self biases, internally self biasing voltage provided to the field effect transistor. Voltage divider biasing indicate that two resistors are used and the combination of two resistors centrally provided the voltage. It is called as voltage divider biasing configuration. Normally, day-to-day life, this type of the configuration indicate that voltage divider biasing configuration majorly used more. Okay. Now we have to be seen the fixed bias configuration first. See, in fixed bias configuration, what we have to do, we have to be apply the fixed voltage, that is VGG, through these devices. But in this case, we have to be considered as IG, means gate current that must be 0. So gate current must is equal to 0, indicate that we doesn't need of the RG and this VGG. So that's why we have to be consider this diagram as like as here. See what it does. It have only the combination of this RG that should be reduced, and VGG it only shows that the whatever the voltage only apply to this type of the configuration, because we doesn't need of this RG, because I equal to 0 indicate that I equal to V upon R, right? So that's why V into R no needed. That's why RG should not be considered. See here, RG is not considered. So normally when we have to be replace this RG, then the circuit is as like as this. Okay, so when we have to be analysis this type of the circuit, in that case what we have to do, we have applying the KVL at input and output side, right? This is input side, this is your output side, right? So during the input side, we have to be apply the KVL. In that case, only two terms, VGG and the VGS, that are coming. Start up with VGG, it is a minus, so minus VGG. Here also plus to the minus, so minus VGS. So minus VGG minus of VGS, which is equal to 0. So it indicates that if minus VGS going on another side, then it is a VGS equal to minus VGG. This is the input thing. Okay, now we have to be calculate the output thing. Means when we are applying the KVL to the output side, it indicates that start up with VDD, end up with here. So plus VDD, current flowing through this RD, that is ID. So plus VDD minus of ID into RD minus of VDS. Okay, these are the things coming with respect to us. Okay, see here, right? VDD minus of ID into RD minus of VDS. Okay, now we have to be use this all the term with respect to VDS. Okay, VDS equal to VDD minus ID into RD. Okay, this is your output equation, right? So analysis of this configuration indicate that we have to be applying the KVL to the input side, KVL to the output side, and accordingly whatever the equation coming, that is the analysis of this type of the configuration. Okay, now we have seen the second configuration, that is self bias configuration. So in case of self bias configuration, we have seen that in this configuration we have applied the two voltages, VGG and the VDD, that are the two voltages applied across your devices. But when we have to be use the self bias configuration, we doesn't need of the two voltages which should be applied for this configuration. Only single voltage that should be required. So it eliminates the need of the two voltages. Okay, so with respect to this, we have applied the VDD to the drain circuit and no voltage is applied between VGS. Only the part of source is again applied to the gate. Okay, this will be in this case. Okay, for the calculation of the self bias configuration, we have applying the KVL at two sides. This is the input side, this is your output side, right? When we have applied the KVL to the input side, it indicates that only two terms are coming, VGS and the this RS. Okay, so this is nothing but a This is nothing but a start up with this loop. This is the main loop. Start up with this loop. Second point, that is a minus. So minus VGS, and then again second point is coming from here. Okay, so current flowing through this RS, it is a IS. Okay, minus VGS, minus of IS into RS, because plus is here, minus is here. So minus VGS, minus of IS into RS. This is nothing but a input equation. Okay, so for that equation we have taking this minus VGS on another side. So VGS equal to minus IS into RS. This is the equation. Okay, so this should be calculated the minus VGS equal to minus IS into RS. But see, in this configuration we have to be known that whatever the current flowing through the drain, that should be exactly flowing through the source. That's why we have taking ID is equal to IS. For the IS we have to be written as a ID here. So see, we have eliminated the IS and taking as a ID. So VGS equal to minus ID into RS. Okay, this is the thing. Okay, now see, this is with respect to the input side. Now we have to be seeing the thing with respect to output side. Output side indicate that this is the equation with respect to your output. Okay, so plus start up with this loop, plus VDD, current flowing through this RD, that is ID. So plus VDD minus of ID into RD, this voltage VDS minus of VDS minus of plus minus of current flowing through the RS, that is IS. Okay, minus of IS into RS, totally I'm telling you, plus VDD minus of ID into RD minus of VDS minus of IS into RS. Okay, this is the equation. Sorry, this is the equation with respect to us. We know that IS is nothing but ID. We have already seen that. So wherever IS is coming, we have to be written as ID. So here is VDD minus of ID into RD minus of VDS minus ID into RS. It should be considered ID into RS. Okay, so that's if you काय प्रॉब्लेम आहे का, लक्षात येते का? प्लीज टेल मी, एनी प्रॉब्लेम? See, for that equation, when we have to be applying KVL to the output side, it indicates that your equation VDD minus ID into RD minus VDS minus IS into RS. We know that IS is nothing but a ID. So for the IS, we have to be written as a ID. Okay. So VD, why we have to be done the same? When we are taking IS as ID, then this ID taking is a common. That's why it is done. Okay, VDD minus of ID into RD minus of VDS minus of ID into RS, because IS is nothing but ID. Okay, so this ID taking common. So VDD minus as it is, this ID as it is, RD plus RS, RD plus RS. Okay, this minus VDS going on another side, that is a plus VDS. Okay, so VDS equal to VDD minus of ID into RD plus RS. This is the equation with respect to us. This is called as also output equation. We have already calculated the input equation. Means analysis indicate that we have to be seen the two things, that is the input, applying KVL to the input and applying KVL to the output and taking out the two equations. We have seen another point, that is voltage or biasing configuration. This is the one of the important of biasing configuration which is all over world, right? See, during this configuration we have to use the two resistors R1 and R2. This is the drain resistor, this is the source resistance. Okay, for that configuration we must consider as a gate current whatever the flow through the device, that is a 0. So that's why I current is 0, indicate that I equal to I equal to VR. So whatever the voltage and resistance, that should be 0, because current is 0, indicate that I equal to V into R. So VRG, which is equal to 0. So RG can be replaced by short circuit. So in that case, these are taking as a one thing, means these R1 and R2 taking as one of the things and taking as RG. They have to be used here, and they have to be taking as a short circuit. Short circuit indicated that it is not indicated. Okay, because no current flowing through the devices, so that Ig equal to V into Rg. So no need of this R1. This is the for the purpose of analysis purpose. Okay, so that's why whatever the voltage provided to this should be called as Thevenin's voltage, VTH. Okay, this VTH is called as phi, also called as VGG. So that should be equivalent voltage which should be coming with respect to here. Okay, this should be directly applied to the gate. Okay, now see, this VDD is again applied to the RD, and all other thing RS that are the same, and whatever the output coming from RSS is again applied to the negative point of your VGS. So here VGG or VTH voltage is nothing but a plus minus voltage that should be applied to the gate terminal of your JFET. Okay, now see, we have to be known one of the important thing. What do you mean by VGG, or how the analysis of the Thevenin's voltage that should be done, right? So to analysis of this VGG, actually this VGG or VTH is nothing but a equivalent voltage which should be coming with respect to this R1 and R2. Okay, so the for that purpose we have to apply the voltage divider rule across it. So it is nothing but a this resistance divided by total resistance into the applied voltage. So it is nothing but R2 divided by R1 plus R2 into applied voltage, that is a VDD. This should be coming as like as VTH. This is equation number 1. Now we have seen that in that equation we have to be seen that whatever the current flowing through the device, that is a 0, right? So this is 0 indicate that we know that V into R J product, that also the 0. That's why we have to be taking it into the short circuit. Okay, now when we have to be apply the configuration, this is the configuration we have to be got. So for that configuration we have applying the initially we have seen this equation. This is the equation how it is coming. Only we have taking same equation number 1. Okay, VGG which is equal to VTH which is equal to R2 divided by R1 plus R2 into VDD. Okay, now we have applying the KVL to this side. This indicate that input side, right? So during this input 3 term are coming. One is VTH, other is VGS, and third is this RS. Okay, now see, this VTH you have to be written as a VTH or the VGG. Okay, we have written as a VGG going from here to the here plus to the minus VGG minus of VGS. Okay, current flowing through this is IS. Okay, IS into RS. This is the plus upper part, lower is minus. So all of the thing is nothing but a VGG minus of VGS minus of IS into RS, which is equal to 0. Right? This is the equation coming with respect to us. Okay, now we have to be taking all of the things with respect to another side, that is minus VGS going on another side. It is a VGS equal to VGG minus IS into RS. Okay, this is the equation, means VGS equal to VGG minus IS into RS. This is the equation, but we know that ID equal to IS. Okay, we have to be putting this thing as a ID. So that's why your equation is nothing but this minus VGS going on another side, that is a plus VGS, which is equal to VGG minus of ID into RS. This is the equation. Now this is the thing with respect to input, but when we have to be applying the KVL to the output side, we have got another equation, that is plus VDD minus, this is the current flowing through the RD, that is ID. So plus VDD minus of ID into RD. This there is a one of the voltage drain to source, that is a VDS, that is a plus minus VDS. The current flowing through this, it is a IS, and current flowing through this RS. Okay, so plus VDD minus of ID into RD minus of VDS minus of IS into RS. Okay, this is the thing with respect to your output equation. Plus VDD minus of ID into RD minus of VDS minus of IS into RS. Again, for the IS we have to be putting as a ID. Okay, so your equation is VDD minus ID into RD minus of VDS minus of ID into RS. Okay, now see, we have putting the same thing with respect to VDS. So VDS equal to VDD minus of ID into RD. Now taking, see, VDD as it is minus of ID taking as a common, ID RD plus RS. Okay, this is the equation with respect to your voltage divider biasing output equation. Now we have seen the actual part of our today's lecture, that is common source field effect transistor. Now see, you know that there are three configuration of transistor. Tell me, normal BJT ची तीन configuration आहेत, कोणती कोणती सांगू शकताय? Please tell me if you know about it. There are three configuration of bipolar junction transistor. Give me the response.
Common emitter, common base.
Right. CE, CB, CC. Is it correct? Common emitter, common base, common collector. Why we have to be done this type of the configuration? See, in some application of your transistor, they have required the large input current, large output current, large input impedance, large output impedance. Means that thing means input impedance, input current, output current. That should be changed, right? Accordingly, that requirement of the current or voltage, we have to use the three type of the configuration, that is common emitter, common base, and the common collector configuration. Okay, so this configuration is same as like as your common emitter configuration, right? Because transistor have three terminal, emitter, base, and collector. Same way your field effect transistor have gate, drain, and source. These are the three terminal. Okay, so in this case, source terminal is, see here, 1, 2, 3. So this is the source, this is a, see, this is the source, this is your gate, and this is your drain terminal. Okay, gate, drain, sorry, gate, drain, and the source. These are the three terminal of the field effect transistor. Okay, now we have taken the common source. So source is here. This should be common. It will be in a input. It will be in a output. Okay, that's why it is called as common source field effect transistor configuration. Okay, just a construct. We have seen the whatever the thing used for the construction of common source field effect transistor. See, in this case, we have applied the input AC supply, that is AC supply is applied across it. RAC is nothing but a series resistor. C1 is called as coupling capacitor. It is used for the purpose of only passing the AC component to this type of the configuration. Okay, VGS indicate that gate to source voltage which should be applied across here, which should be used for the purpose of increasing or decreasing the depletion area of your field effect transistor. It is nothing but a reverse bias voltage increasing or decreasing. That's why VGS is used. Then whatever the voltage or current applied across here, accordingly there should be generation of the current, that is the drain current, and VDD. VDD indicate that plus VDD voltage is applied for the operation of this field effect transistor. Okay, whatever the voltage applied, opposite voltage is coming across here. Why? It is same as like as your transistor. I'm explaining you the same thing. Now see here, this is the diagram, actually diagram. For that diagram, this is the input AC supply, right? Input AC supply indicate that we have applied the sine wave to this type of the configuration, sine wave to this type of the configuration. Okay, now whatever the VGS indicate that negative voltage is applied. Okay, so negative voltage indicate that this is the minus voltage, minus, right, applied across your field effect transistor. Okay, due to that minus voltage is applied across here, it should be increases the depletion area with respect to field effect transistor. Okay, that's why it is a negative voltage. See below the this line, negative voltage. Then IDQ indicate that drain current. So drain current flow. See, one of them I am explain the working of it, and then I have to tell you the diagram thing with respect to drain current, right? See, याच्यासाठी आपण काय करतोय सांगतो, इनपुटला एसी सिग्नल आपण अप्लाय करतो, राईट? एसी सिग्नल अप्लाय केलेले असते थ्रू द सिरीज रेजिस्टन्स, कारण जर याची लेवल कमी जास्त झाली तर त्याचा इफेक्ट तुमच्या पुढच्या सर्किट होऊ नये यासाठी आपण ते रेजिस्टन्सच्या सिरीज मधून त्याला अप्लाय करतो. ओके, नऊ पुढे जाऊन ते सिग्नल आपण कॅपॅसिटरला अप्लाय करतो. कॅपॅसिटर का अप्लाय करतो लक्षात घ्या, जेणेकरून जर त्याच्यातनं डीसी सिग्नल काय आली ते एलिमिनेट होईल, ओनली एसी सिग्नल पुढे पास व्हावी यासाठी आपण यूज करतोय. त्याच्यानंतर VGS हे व्होल्टेज यासाठी अप्लाय करतोय आपण की जेणेकरून काय होतं, फक्त याच्यामुळं तुमचा डिप्लेशन एरिया म्हणजे करंट कंडक्शनचा एरिया कमी किंवा जास्त केला जातो आणि इथं तुमचा ऍक्च्युली आउटपुट मिळतं. पहा, see now we have to be seen the things working of this configuration. We have applied the input AC supply to this type of the configuration. It will be provided through the RC, and C1 is capacitor which is used for the purpose of only passing the AC signal to this configuration. This VGS indicating that it should be provided the reverse bias voltage that should be more or less accordingly. It should be increase or decrease the depletion area. Okay, now whatever the voltage, see input AC supply voltage which should be applied across here. Okay, so due to the application of this input voltage, that is a AC voltage which should be applied across here. So what happened, it have its current gain capacity. See, this junction field effect transistor have its own current gain capacity. It indicates that whatever the input applied in some times, sometimes indicate that किती input apply करतो त्याच्या पट्टीमध्ये. Sometimes input should be increases over here, but that value should be decided by the manufacturer of the particular field effect transistor. Okay, now consider that here we have to be applied the 2. Normal 2 is the value of the input applied. Here we got the 12 over, indicate that 12 over as a output. Okay, so what it indicate that whatever the input applied across here, that should be increases here 6 times. Okay, right, this should be coming across here. But what happens, see, one of the important thing with respect to this, why the output is opposite to the input. See, we have applied input to, we have got the output as a 12 normalized value we have taken as example. So 12 is applied across here, but see, this is the whatever the output coming, that is in the form of voltage and current internally. Okay, so due to that, the voltage and the current coming across here, the resistance is nearby it. So whatever the voltage coming, the same voltage should be dropped by this RD resistance, right? So whatever the voltage coming, that should be dropped by this RD, right? This drain resistance. So current is as it is. So we have applied the positive current. We also got the positive going current across this, right? So in that case, what happen, whatever the voltage coming, that should be dropped by this RD. So it indicate that whatever the voltage, म्हणजे जेवढं काय व्होल्टेज होतं ते सगळं इथे ड्रॉप केलंय, त्यामुळे त्याच्या अपोजिट व्होल्टेज इथे येणार आहे. लक्षात घ्या. मग काय पॉझिटिव्ह गोईंग असेल तर निगेटिव्ह गोईंग येणार. हा, निगेटिव्ह गोईंग व्होल्टेज, कारण तेवढं सगळं ड्रॉप केलेलं इकडं, राईट? सो दॅट वी गॉट द निगेटिव्ह गोईंग व्होल्टेज. This will be happen with respect to your voltage. Another thing, when we have applied the C, this is with respect to the positive half cycle. We have seen that second negative half cycle, right? Second negative half cycle applied across heat, right? So second negative half cycle applied across it, it indicate that whatever the output coming, see, whatever the output coming across here, input coming, consider as a 1, consider as a 1, right? So less amount of voltage applied across input, so we got the less amount of output voltage, because gain also less. 6 consider as a voltage is coming across here. Okay, 6 is coming across here. What it indicate that less voltage is applied across here. So what happen, opposite way. So this is not drop any voltage. Okay, so same voltage means whatever the voltage is coming across here, that all of the voltage is coming across your output. So that's why this 6 is coming across here. So this positive going voltage is appear across here. See, only thing is coming with respect to this type of the configuration, whatever the voltage applied across it, it should be dropped by this resistance. In a only case we got the output voltage is less. When it doesn't drop the voltage, in that case we have got the largest voltage. That's why if we apply the sine wave, we got the output as a cos wave. That is the reason behind it is. हे लक्षात आलंय का? कॉमन सोर्स FET एम्प्लिफायर जे व्होल्टेज अपोजिट काय येतं सांगा मला, मला सांगता येईल? समजलंय का सांगा, का परत सांगावं लागेल एकदा? प्लीज रिप्लाय. हा, लक्षात आलंय का? प्लीज रिप्लाय द येस और नो. एक 5-6 वाक्यात मी रिपीट करतो. वर्किंग सी, आपण याचं वर्किंग पाहत असताना काय करणार आहोत, आपण जे इनपुट एक्सेस अप्लाय केला ना, त्या RS आणि C1 थ्रू आपण याला इनपुटला अप्लाय करतो. ऍक्च्युअली लक्षात घ्या, तो अप्लाय केलेला व्होल्टेज इथं विदाउट फिजेस कन्सिडर करायचा. अप्लाय केलेलं व्होल्टेज समजा इथं 2 अप्लाय केलेलं, लक्षात घ्या, पॉझिटिव्ह गोईंग 2 एवढं व्होल्टेज आपण अप्लाय केलेलं आहे, राईट. त्यामुळे काय होणार आहे, याची गेन जर 6 असेल तर 12 एवढं व्होल्टेज तुम्हाला इथे मिळणार आहे. ओके, पण काय आहे, ते व्होल्टेज हे विथ रिस्पेक्ट टू ह्या रेजिस्टन्सचे असणार आहे, राईट. तर रेजिस्टन्सची कंडिशन काय, की तो जे व्होल्टेज येतो ते ड्रॉप करतो, लक्षात घ्या. त्यामुळे काय होणार आहे, पॉझिटिव्ह गोईंग स्टेजला जे व्होल्टेज अप्लाय केलं ना, ते सगळं व्होल्टेज इथं ड्रॉप होणार आहे. पण त्यावेळेस करंट तो कुठलाही ड्रॉप करत नाही, लक्षात घ्या. त्यामुळे करंटची लेवल जी आहे ना, इथं पहा, करंटची लेवल जी आहे ते ऍज इट इज राहते, करंटची लेवल ऍज इट इज राहते. पण व्होल्टेज वर ड्रॉप केल्यामुळे ते अपोजिटली डिक्रीजिंग होत राहतं, पहा, राईट, इथपर्यंत. ओके, त्यानंतर काय होतं, पहिल्या वेळेस निगेटिव्ह पॉझिटिव्ह हाफ सायकल अप्लाय केलं तर निगेटिव्ह मिळालं. दुसऱ्या वेळेस काय होणार आहे, निगेटिव्ह हाफ सायकल आपण अप्लाय करतो, राईट. निगेटिव्ह हाफ सायकल इथं अप्लाय केल्यावर काय होणार, थ्रू द RS आणि C1 ते व्होल्टेज पुढे पास होणार आहे. पुढे पास झाल्यानंतर काय होईल, इथं व्होल्टेज पास झाल्यानंतर हा जो काय करणार आहे सांगतो, जे व्होल्टेज अप्लाय केलेलं ना ते लेस व्होल्टेज आहे, लक्षात घ्या. त्यामुळे लेस व्होल्टेज मुळे तेवढं पट तुमचं जे अप्लाय केलेलं व्होल्टेज तेवढं पण तिथं इन्क्रीज होऊन इथे मिळालं, लक्षात घ्या. इथे इन्क्रीज होऊन मिळालं. पण लक्षात घ्या, आता काय झालंय, अप्लाय केलं निगेटिव्ह हाफ सायकल होतं, लक्षात घ्या, निगेटिव्ह हाफ सायकल होतं. त्यामुळे इथं लेस व्होल्टेज मिळालंय, त्यामुळे हा सुद्धा लेस ड्रॉप म्हणजे ओढून गेल व्होल्टेज, लक्षात घ्या. त्यामुळे इथं काय होणार आहे, मोर व्होल्टेज तुमच्या आउटपुटला मिळणार आहे. त्यामुळे इथं पॉझिटिव्ह हाफ सायकल मिळतं, लक्षात घ्या. दिस इज द थिंग. आता तर लक्षात आलं की नाही?
Yes, sir.
ओके, हे परत एकदा सांगतो. AC, this is the input AC supply applied across it. Minus VGS indicate that we have applied the reverse voltage, negative voltage to this. That's why it is below to the line. Okay, IDQ indicate that we have to be known that either your voltage that should be increase and decrease means opposite, but there should not be change with respect to the current. We have seen that. Okay, so level of this is same voltage. If the current is increasing upward, it should be decreases, right? Opposite thing will be happen with respect to your voltage. So this is the whatever the output coming across your devices, that is nothing but your voltage. See, now we have seen up to now the one of the important configuration junction field effect transistor, right? Some of the disadvantages of the JFET, right? What it indicates that it doesn't do any other thing. म्हणजे सांग कामे म्हणतात मराठीमध्ये, त्यासारखं काम करता येईल. म्हणजे काय, सी, इट शुड बी आयदर युअर increasing and decreasing the depletion layer only, right? This is the work of your field effect transistor, right? We have required more than that of that. So that's why we have designed one of the other devices that is called as field effect transistor. But for that construction, we have used the other material, that is metal oxide semiconductor. Okay, so that's why it is called as metal oxide semiconductor field effect transistor. There are two types of the MOSFET. See, normally there are two type of, see, this is the MOSFET. There are two type of the MOSFET. One is D MOSFET and other is E MOSFET. Now see, D MOSFET is same as like as your normal field effect transistor, right? E MOSFET, D indicate the depletion type MOSFET. Okay, means in this case also increase or decrease of the depletion layer. That's why it is called as depletion MOSFET, and it is same as like as field effect transistor. Means your MOSFET should be work in a two condition, that is depletion type MOSFET or enhancement type. Indicate that enhancement type of the MOSFET. Okay, accordingly there are D MOSFET have the two type, that is N channel and the P channel. Channel indicate that the area, see, the area which should be used for the purpose of the current conduction. See, as we have to be increases the area for the current conduction, more and more current flowing through the device, so it should be act as like as forward bias, right? So it indicate that whatever the whatever the voltage applied across your reverse bias, it decided the size of the particular configuration. Okay, now see E MOSFET, enhancement type MOSFET, it also have two type, that is N channel and P channel. Okay, N channel indicate that N material used for the construction of channel. P channel indicate that P material used for the construction of the particular channel. Okay, we have seen the symbol of it. For the depletion type MOSFET, we have seen this diagram. Okay, so in that diagram there should not be see point in between three, right? Means dotted line indicate that it is a enhanced type of the MOSFET. Normalized, it indicate that depletion type of the MOSFET. Okay, see there are two type, N channel and P channel. N channel indicate that we have seen that this configuration, N indicate that arrow towards the under, P channel indicate that arrow towards the outer. Okay, साधे ट्रिक सांगतोय लक्षात ठेवायचा. पी बाहेर जाणारा पी कन्सिडर करायचा, त्याच्या अपोजिट एन असतं, एवढं लक्षात ठेवायचं. ओके, सो एन चॅनल डी MOSFET indicate that in that case arrow towards the internal, in case of P channel arrow towards the outward. Okay, and the difference between D MOSFET and A MOSFET is that in case of D MOSFET, whatever the line used for the symbol, that is a continuous. In case of your D MOSFET, in case of N channel, E MOSFET, the whatever the line internally used, that should be dotted line. Okay, see whatever the thing I am telling you, that should be discussed over here. See, the main disadvantages of the JPT is that it is operated only in the depletion mode. Right, depletion mode indicate that it should only increase or decreases the depletion layer. Right, so increases and decreases of the depletion layer indicate that it should be increase or decreases only the size of the channel. Right, that is the thing with respect to your junction field effect transistor. Right, this is the disadvantages, because only one work that should be done by this junction field effect transistor. That's why we have designing the sum of the devices. We should done the particular thing, means it will does the all of the work, right? Which is nothing but it should be either act as a depletion type or enhancement type, right? Depletion indicate that increasing and decreasing the size of the channel, and E means enhancement of the size of the channel, right? These accordingly there are D and E type of the MOSFET. Okay, any problem related to the symbol stage of the D and E MOSFET? कुणाला काय याच्याबद्दल शंका आहे? आणि डिसएडवांटेजेस त्याच्या रिस्पेक्ट टू हा बोला, कुणाला काय सांगायचंय का? सीमाला घे. Please tell me any problem. No. कुणाला काय याच्याबद्दल बोलायचं आहे का? MOSFET आणि त्याच्या टाइप बद्दल
परत सांगा सर.
Okay. See, MOSFET normally indicate that metal oxide semiconductor field effect transistor. Okay, metal oxide semiconductor field effect transistor have the two type, that is depletion type MOSFET and the other is enhancement type of the MOSFET. Now see, why the name depletion and why the name of enhancement? The reason behind it is depletion indicate that increasing and the decreasing of the size of the depletion layer with respect to your PN junction down. This thing happen in case of D type MOSFET. Same thing will be happen with respect to your field effect transistor. That's why D MOSFET is also called as field effect transistor. Okay, so accordingly D MOSFET have the two type, that is N channel and the P channel. Okay, enhancement type MOSFET also have two type, that is N channel and the P channel. But see, during this D MOSFET consideration, we have seen that whatever the whatever the gate signal applied across, it is still as a continuous, but in case of this configuration, it should be taking as an dotted line. The reason behind it is we have discussed in a further session, but The reason mandate is it indicate that it is a enhancement type of the MOSFET. Okay, see, for the purpose of this configuration, we know important condition, that is a when we have to be use the MOSFET for our application. Why we not use the FET for our application? Because see, FET indicate that it has so only one change, only one thing they have to be done, that is a it should be increase or decrease the size of the depletion area. Okay, so accordingly means either you are increasing or the depletion area, it indicate that by changing the reverse bias it should be worked, no any other function it should be done, right? That's why we consider this is as an disadvantageous thing with respect to your configuration field effect transistor configuration. So that's why we have designed the metal oxide semiconductor field effect transistor. It have two-way working, that is either your depletion type or the MOSFET type. Depletion type means either you have to changing the depletion area of the MOSFET or the either increasing the area of the operation of your enhancement type of the MOSFET. This is the thing happen with respect to E type of the MOSFET. लक्षात आलंय का आता? Please reply. इथं डिटेल काहीच म्हणजे फक्त कन्स्ट्रक्शनल थिंग आणि सिम्बॉलिक थिंग आहे, त्याच्यामध्ये फक्त डी आणि ई मॉस्फेट नेमकं याच्यामध्ये काय डिफरन्स आहे हे फक्त आपल्याला माहिती करून घ्यायचं, लक्षात घ्या. बाकी सगळे एन चॅनल टी चॅनल दोन्ही पण आहेत. फक्त डिप्लेशन टाइप मॉस्फेट मध्ये कन्सेप्ट ऑफ डिप्लेशन ऑफ द वॉट एव्हर द लेयर that should be discussed. In case of enhancement जास्त डिटेल नाही, एनहान्सिंग ऑफ द चॅनल एवढं फक्त डिस्कस केलं आपण. ओके, see, we have to be seen the one of the important part, that is construction of the n channel D MOSFET, right? So construction indicate that what will be the difference between your field effect transistor and this type of the configuration, that we have to be seen the first, right? So in this configuration, we have seen that only in case of your field effect transistor, only P and PN that should be used, right? Two small P layer or two small N layer. See the diagram. See, in case of this type of the configuration, that is FET, we have to use the P layer, one of the P layer, two P layer in between one N channel is used, but only this type of the configuration. But in this configuration, what we have to do? In that case, we have taking P as a whole substrate. Substrate indicates that one of the layer of this type of the configuration, and all other thing as an N layer. Okay, this is no large amount of channel is not used here. Only this portion in between two N, the small portion used as the channel for current conduction across here. Okay, now see, it have three or more terminals. See, one of the important thing with respect to it doesn't have only three terminals, it have three or four. Why it is? See, in some application we have required the four terminal. In that case, this type of the configuration you have to use the four terminal. See, you have to be use the three terminal for your application by this configuration, but it have four the terminal. Okay, see, if we have to be connected one of the ohmic contact with a particular P terminal, that is called as substrate terminal, right? This is nothing but a substrate terminal. Okay, here we have to be connected one of the important element, that is a gate terminal, right? So gate terminal is directly attached with this layer. This layer is called as SiO2 layer. SiO2 indicate that silicon dioxide layer. Okay, silicon dioxide layer we have directly connected, and this should act as a gate terminal. Okay, now see here two N layer connected with respect to upward and lower side of this type of the configuration. Middle layer is called as a channel layer. This is used for the current conduction purposes. Okay, see, After all, this n layer connected by outer section by this ohmic contact, this is also called as the drain terminal. Okay, drain terminal. After all, this terminal means lower part of this configuration connected through the ohmic contact to the internal n, that should be called as source. So get drain source with substrate, that are the four terminal of your D MOSFET. Okay, see, figure shows that the actually constructional thing, right? Normally all of the devices with respect to the BJT, see, when we have to be considered the thing with respect to the BJT, it is called as bipolar junction transistor. Okay, in case of bipolar junction transistor, we know that emitter base character, that are the three terminal, but in this case we know that there is a one of the extra terminal, that is a substrate terminal internally, that should be connected. See, it has substrate terminal internally, this terminal, see, this substrate terminal should be connected to the source terminal of the devices, right? Source terminal of the devices. But some devices means in some application we need of the four terminal, that's why this substrate terminal added to the devices. Okay, this substrate terminal internally connected to the source terminal of the device. Okay, this is the thing with respect to the normalized construction of this n channel D MOSFET. Why it is called as n channel? Tell me the reason behind it is. I have already explained the same thing. Why it is called as n channel? Please tell me. Why it is called as n channel? See the diagram and tell me. Where is channel? See, in case of field effect transistor, channel is middle portion. 2p, there should be one of the middle portion, it indicates that channel. Here also channel. See, this substrate is act as a channel. Is it correct? I am already substrate is act as a channel. Is it correct? A चे कोण सांगेल का? Where is channel? Either this substrate act as a channel. Please tell me. Pradhamane, please tell me. Where is the channel for this? I am already told you related to the channel. See, P indicate that substrate area. This should not be act as a channel. Channel indicate that this is used for the current conduction from your source to the drain terminal. Okay, so for that purposes, in this configuration, we have to be arrange the same thing. Means in between 2n, there should be one of the smallest area. This area is called as channel. This is the thing with respect to your depletion type of the MOSFET. That is the change with respect to your field effect transistor. Field effect transistor, if you have to be constructed, in that case, largest 2n or 2p area, in between that there is a channel. Okay, but here is a small channel in between 2n section. Okay, see, here are, I already explained the thing which are here used. Normally one thing, as I remaining only this terminal and this terminal. I am already, it also tell source terminal, substrate terminal and source terminal, that are internally connected to each other, right? Source and the substrate terminal. This is nothing but a this terminal, one terminal. Okay, all other things are same. Due to this, see here SiO2 layer, due to that SiO2 layer, whatever the component connected across here, that should not be directly connected to the internal part. They have connected through the SiO2 layer, right? It have its own region, right? Drain, source and gate, these are terminal not connected directly. It should be connected through the this SiO2 layer. Okay. Again, I'm within a 1 minute. I will explain the construction of N channel D MOSFET. See, N channel indicate that it is the device means D MOSFET which have the electron or major. Why electron or major in case of N channel? Please tell me. Why electron are major in case of N channel D MOSFET? Please tell me why N is or electron is more in case of this step. आता मी